Welcome to the Bit of a Tangent podcast. I'm Jared, and it's been several months since I've recorded one of these introductions for the podcast. So thank you to my co-host Gianluca for stepping in. It's much appreciated. It is March of 2020, which is frankly frightening. I hope your New Year's resolutions are going better than mine. Well, anyway, on this episode of Bit of a Tangent, Gianluca and I discuss the emerging field of self-supervised or semi-supervised machine learning. This is an immensely exciting and active area of machine learning and AI research, and it's probably one which most people might not have even heard about before. So we build up to the intuition for this topic by distinguishing between supervised and unsupervised learning. We discuss autoencoders and dimensionality reduction, and we actually end up exploring in real time how these techniques could be used in a quantified self project. This is something that Gianluca is particularly passionate about, and I think you'll hear that in the interview, where he sort of muses about how some of these techniques could be used on his N of 1 sleep quality dataset. The episode culminates in a fairly detailed discussion of the Contrastive Predictive Coding, or CPC model, and how this model allows us to learn about the structure of the world, the structure of, in this case, natural images, without tons of labeled training data, a problem which machine learning, as I'm sure you'll hear in the episode, really struggles with. So this one was a lot of fun, and it was certainly an exercise in realizing just how much more there is to learn, at least for me personally. It's always really easy to see the gaping holes in your knowledge of something when you are trying to explain it to someone else. So I hope that you enjoy going on that journey with me. And with that, enjoy the episode of Bit of a Tangent. All right. So potential topics for today.
What the fuck are we going to talk about?
I mean, I was actually thinking when I was pouring this glass of wine, I was thinking I need to have more bad shit happen in my life so that I can buy another bottle of wine or potentially whiskey next time, I'm thinking, frankly.
That could be good.
And just sit here and chat shit to you and drink it. That went really well. I enjoyed that. That was very fun.
Yeah, man. I think it would be cool to do another, maybe a drunk episode.
Yeah. Tim Ferriss inspiration.
Could be fun.
But I was thinking, as I was saying, I think some possible topics, we can talk about maybe some of the stuff that Eric Weinstein's doing with his podcast, just because it's been a mind blow recently. We could talk a little bit about this self-supervised learning stuff that I did my final project for that summer school in. Obviously not an expert, but like the general idea is something we've actually discussed before when me, you, and Tom met up and like had a discussion of different like directions in AI research that are interesting. And like this whole self-supervised bootstrapping thing is super cool to me.
Totally. Yeah, that'd be really cool. That's also something I'm interested in because I might be looking into some of that for my project as well. So
yeah, I was thinking
that is a
small
topic.
Data, so it'll be the perfect domain.
This essay that I'm writing at the moment is the working title is "Artificial Inadequacy: Why Humanity is Probably Fucked." And I'm hoping I can adapt some of the body of it into a less wrong post at some point. But the core sort of thesis of it is actually that there's the control problem in AI, and that will help address a lot of AI risk. But fundamentally, that is nothing without good coordination for human institutions and systems, because you can have solved AI alignment, but if not everyone implements the solution, then you're still fucked. You still live in the world where people can make nuclear weapons in the microwave.
Well, I mean, you are sneaking in the assumption there that like AI is doable by one person or a small group.
Yes. So if we go into it, I've got a more controlled flow of argumentation. But anyways, the core point being that it's this problem of coordination sort of overrules. So I don't know if we speak about this, I'll go and cover the sort of inferential steps a bit more in a bit more detail. But the sort of key point is that I almost see there's this pattern, right? So fundamentally, the control problem is almost entirely subsumed by the coordination problem, or maybe entirely subsumed. And so what we really want to be working on, I think, is a generalizable solution to the coordination problem. Because if we can solve control but not coordination, it might not be very useful, because then we're still at risk of various things. And if we can generalizably solve coordination, not only can we then solve control and in general mitigate AI risks, we can also deal with all the other kinds of existential threats that humanity faces because of our inability to coordinate at scale, like man-made climate change, bioterrorism, those kind of things. So that could be something to discuss, although it may be better for another episode where we give some more background on game theory and maybe talk about the quadratic voting and all those kinds of topics.
Yeah, okay. Well, I definitely agree that the control problem is a sort of sub-problem, or it's kind of a special case of the coordination problem, I think. I think that if you can just view us as having some ends, like we're trying to get this AI to cooperate with us, which is just, the coordination problem, as we've talked about so many times on the show. And I think it kind of makes sense that it's such an overarching theme that we keep coming back to, because I think both of us would love to see that as a problem that gets solved, or at least that we have better mechanisms of dealing with. As for, I don't know, I just feel, whenever I think about the damn problem, I just feel helpless though.
Yeah, honestly, I keep getting to the stage where I increasingly value how important coordination is, and also increasingly find how it just is never achieved. Like everyone seems to just default to, regulation, but that deciding to regulate and determining what to regulate and how you'll enforce it is a whole other coordination problem. So you're just shifting the problem one rung up the ladder, right? So it's like saying I'm going to clean up my spilled coffee by throwing some spilled tea on it. Like you're solving the problem by just moving the problem somewhere else, right? So yeah, I mean, I can only identify like two cases where coordination gets bypassed. It's not solved, it's bypassed. The one is by having some kind of player, some single entity who's above the whole game and outside of the game and can just top-down regulate it. So like in a monarchy. And the other case is with people, with individual agents in certain games foregoing their own best strategy in order to serve some greater good, right? So like when you see journalists go to jail or get executed because they expose some governmental secrets that are to do with abuses of power or things like that, or they're foregoing their own best interest in service of some greater good. That is cheating the game by breaking the Nash equilibrium. But I don't think that works at scale. It's an act of martyrdom.
Maybe from what you're saying there's a case in which maybe the control problem isn't actually a sub-problem of coordination. If you view it as human coordination could be solved, I mean, possibly by some form of AI, right? Which could be this external, I mean, I think in the prisoner's dilemma, you just call it like the mob boss, right? The person who can enforce some kind of outcome.
And in an ideal world, that's the form regulation would take. It would act as that outside of the game entity, but regulation has to come from somewhere. And that's where the coordination issues come back in. So yeah, I think I see where you're going, but finish your idea.
Yeah, so I mean, I guess we could solve maybe many of our coordination problems internal to human society by making an AI sort of this non-human external entity. But then you have the larger problem, which is that creating an AI that will help us with our coordination problems is a control problem. So I guess what I'm really doing here is just figuring out how these two problems relate, not so much offering anything useful about them.
Yeah, no, I mean, it's an interesting idea. I think like one of the interesting approaches I've seen to solving control is to have these kind of systems whereby a large part of the problem of control is just blind function optimizers doing their thing effectively, and that thing is generally never aligned with what the actual interests or goals are. And so there's this idea of like almost learning those values in a dynamic way where the AI is never really sure of what it is that you want. And so it's always reluctant to do too extreme a thing because it's not entirely sure that it's correctly estimated what your values are. So there's like, what's the system called? I think it's called like reverse cooperative reinforcement learning, where you've essentially got like AIs in this game with humans and they're constantly sort of giving feedback. So the AI is like estimating what it thinks the human wants, doing some things towards that goal, and then responding to the sort of loss that comes from the human rating how much they approve or disapprove of that action. And so there are some interesting things like that where you can almost learn human values as like some complex state space or something like that. And so it could be an interesting one, but so we're almost saying like, yeah, you could instead reframe it as control dominates the coordination problem, because you could use AI to solve coordination for every case other than control, and then we just would need a solution to control. And then the question is just like, which one is making more assumptions? Because let's say you can't solve coordination in a generalizable way. Like let's say we find some proof that that's mathematically impossible. Well, then the other one's our only hope. But yeah, until we have more data on it. Anyway, and I think the fact that only like a few dozen people are actually working on this problem or these sets of problems seriously in the whole world is kind of scary when you consider that like maybe millions of people are working on AI development in various forms.
Yeah, although I would be surprised if those millions of people are really working on sort of general AI. I think.
So that's my other thing, is that I don't think you need general AI to have.
You don't think you need general AI to have this problem?
One of the arguments I make in this article is that you don't need general intelligence to have the really negative side effects that come from AI. Like you can paperclip the situation with a pretty narrow AI. It just has to have like some function and be able to do different kinds of things in different combinations in order to try and achieve that function. But I think maybe what I'd ideally like to do is sort of finish this in its assignment form that sort of checks all the boxes for the assignment and submit that, but then rework some of the core arguments into a maybe less wrong post, otherwise just a blog post of some kind, and then maybe get your feedback on that, and then we build it into an episode topic from there. But yeah, and so then maybe in the meantime we should chat about some of the stuff that you've been working on, and the I forget the term you used for it, but the sort of data augmentation, bootstrapping type methods. That could be some interesting.
Maybe we can motivate maybe the general distinction between supervised and unsupervised learning, and then this sort of weird hybrid category of self-supervised learning. I can't say that for some reason. It's just in the realm of things I can't pronounce.
It's fine. That's what the wonder of editing magic is for.
Yeah, if I sound coherent.
Yeah, you're self-supervising too much.
And so we can motivate why this is an interesting and useful way to do machine learning. And then we can talk about some of the specific techniques. And the one that I have a little bit, and I mean a little bit more experience, is because I sort of worked on one of the newer ones in this last week of the summer school. and it was just really, really interesting. And the best part about it is that, at least in my head, it's fairly explainable. Like, there are lots of things which are not explainable without a good YouTube video or a lot of skill, but this one is fairly amenable to just imagination and good audio descriptions.
Let's do it.
Yeah, so I mean, why don't you give me just the basics of like supervised versus unsupervised learning, and then we'll place this idea of self-supervision into context.
Sounds good. So I think maybe a nice way to do this is to give sort of the simplest, maybe oversimplified version of an explanation, and then add the complexity in, right? Because then there's a good tangible grounding that you can work with. So supervised learning is a means of machine learning where you have a whole bunch of data and it's labeled with some kind of field that you care about, right? So let us say, let's go for a canonical example here. So imagine you have a massive data set of millions of pictures of cats and dogs, and you want to train a machine learning system to be able to tell if there's a dog in a picture or a cat in a picture when it sees a picture. So what you do is you have this gigantic data set, and then you have to go and label the images in the data set with the tag cat or with the tag dog, so that you have that information to train the network on, because there's no way to inherently like imbue it with that information in this paradigm. So you've got all of these millions of pictures of cats and dogs, and most of the time it involves getting people to go and manually label them. So someone's got some computer program open that flashes a picture and they have to click is a cat, is a dog, or some other such labeling system like that. So you go and hand label it, or you maybe scrape the data from people's social media or whatever you might do, from publicly available images that have tags on them already. But mostly these tags, well, they all had to come from humans at some point, right? So then you've got this data set and it's got this labeled feature, this field that is what type of animal the thing is. In this case, it's either cat or it's dog. And then what you do is you repeatedly show your information processing system, so let's say a deep learning network, these images, and you show each image with its associated label, and you start building up these statistical associations between the two. And you do this for thousands or maybe millions of iterations, and then after that, you give it images with no labels, and you see if it can correctly label them. So you give it a picture of a cat that it's never seen before, and you see if it can correctly identify it as a cat, even if you haven't obviously given it that label. So that's supervised learning. The supervision comes in the sense of you've given it this syllabus to learn from, this data set of labeled data, right, that you can then say, this is the thing we care about, and this is what the right answers are. And then it just sort of learns it by kind of brute force.
Do you want to say more maybe about just this basic idea of training? So running some image through, getting a prediction, and then this idea of using backprop to make your predictions go more in the right direction almost.
Yeah, so I think so how the learning happens is obviously different depending on what kind of system you're using. So predominantly, at least in the example I've given of dogs and cats, you're going to be using something like a convolutional neural network, right? Which is a deep learning neural network. And so the learning there happens through backpropagation. You look at, you quantify how wrong the prediction was, and then you use that information to update the parameters in this network so that in future it would be closer to the correct prediction. But for instance, the same paradigm applies when you're doing like a linear regression model, which predates deep learning by, decades. A linear regression model is doing the same thing. It's just not doing it with backpropagation. So the learning can be anything there. But for most interesting problems that are being tackled today in interesting ways, it's with deep networks, and those pretty much exclusively train with some version of backpropagation. I don't, is that getting at what you were?
That's ideal. So now, what about when people talk about unsupervised machine learning techniques? This is definitely something that you've had lots more experience with than I have. I've done mostly supervised stuff. So what's the general idea there? Obviously, people can intuitively hear from the name that somehow it's got to be quote unquote learning by itself, but what does that usually look like, and what are the main algorithms that do that?
Yeah, so this is a really interesting one, and obviously, as you can hear, there's a difference between supervised and unsupervised learning is, well, now you suddenly don't have those labels anymore. So, okay, well, how the hell does the system manage to do anything useful if we can't tell it what we care about it doing? And that's the main challenge of unsupervised learning. So maybe a nice example here would be you give it a whole bunch of images and cats and dogs, and they've got no labels because we just found these images by scraping from the web and we couldn't be bothered to go and label them. And we're like, well, let's see if it can figure out how to tell the difference between these two things. It might not know that we call them cat and dog, but that's fine. Can it just tell the difference between these two clumps of things? So then what you would do is you would have it analyze sort of the properties of the data, and by comparing kinds of values, you would do something like clustering, right? So if you imagine some kind of like scatter plot with two clusters of dots that are sort of grouped independently that you could draw a line between, right? They're kind of like separable clusters. That's the kind of thing you're going for. So if we're trying to get it to tell the difference between the cat and dog images, we'd hope for, like, say, at least two clusters there, that it was identifying differences. And maybe those are things to do with, dogs on more generally certain kinds of colors and textures, and it might pick up on properties like that in the data. It's generally not the kind of thing you achieve with images. It would be really hard to do it with images, I think, and you need some pretty bespoke methods for that.
Is that because just the dimensionality is too high, or because like the dimensionality of the image is so high, to draw that boundary is really difficult, so you need this kind of supervised deep learning approach, or is there another reason?
Yeah, you probably get a whole bunch of things like vanishing gradients and issues like that, which CNNs that we spoke about in supervised learning can address really well because of the ways they're structured. So, I mean, you could combine the two. You could take like a pre-trained convolutional neural network and then use the output sort of features from that to do unsupervised learning. But we're getting into the complexity of this here. So often this takes the form, like one that people might have heard of is principal component analysis.
Yeah.
PCA. So this is a form of unsupervised learning. And it's really useful. I kind of think of it as the linear regression of unsupervised learning, right? So what linear regression is to supervised learning, PCA is to unsupervised learning. It's like the more old school statistical technique. And essentially what the term that gets thrown around with unsupervised learning is often dimensionality reduction, right? And we've touched on this before, like back in, I think, like episode 2 or 3. But essentially imagine you've got a massive spreadsheet, right, that represents your data set. Just useful to think about it like that. Every column that you have is called a feature, or every column that you have is called a feature. And each of those features can be thought of as a dimension in some multidimensional scatter plot, right? So if you just have one, or if you just have two columns of values, then you can imagine that being X and Y on a two-dimensional scatter plot, right? And then you can see how you might get clusters there. But traditionally, you're going to have, dozens, hundreds, maybe thousands of these columns, these features. So in the case of images, every single pixel is a feature, right? Or maybe even 3 features, depending on how you've encoded it, right? And so with modern image resolutions, that's a lot of features, and that's where the difficulty can come in. But for a lot of problems, you've got maybe 100 or 1,000 features, and you want to condense these into these new imaginary features that encode all the variance, right? Because to create clusters of things, what you want to do is you want to find some way of representing them that maximizes the dissimilarities and minimizes the similarities. So the things that are consistent properties of a cluster will be closely spaced together, and the differences will be spread out as much as possible. So you might take something that's came from a spreadsheet with 100 columns and through these techniques collapse it into 3 or 2 columns, at least if you're going to be inspecting it visually, because humans can't really work with 4-dimensional or higher spaces. Right, so the point I was getting at is that unsupervised learning is a way of finding patterns in your data without having to have explicit labels that you've gone and put on there. It's a way of finding properties without telling the algorithm what's important. And it's very useful because A, you don't have to label things. B, you might not want to enforce labels on things. Like you might not know what you want to label things as. There might be no idea like cat or dog that neatly combines all of the features of something. It might be some total abstract cluster. And so you just want to see that. And so like a prime example of this might be to, if you're running like an e-commerce site or you're running like you're running some kind of retail chain, you could collect all the data you have from the spending habits of your different customers, and you could do this dimensionality reduction through some form of unsupervised learning, and you might find you have like, say, 5 different clusters that come out, right? And these represent your 5 different kinds of customer. And then what you can go do is you can dig into each of those clusters and start looking at samples from that cluster and finding ways of making sense of what those clusters are. Because the clusters make sense statistically, algorithmically, but they don't necessarily correspond to things that humans can label with a word, right? But maybe you start looking into it and you find one cluster is like, 40-year-old white men, and another cluster is like 15-year-old girls of all different ethnic backgrounds, right? So you find all these different clusters, and presumably there are relationships between people's age and geographic location and socioeconomic background and the things they buy, and that's the pattern that you're picking up on. And so that would be a use case that you might apply it to there. So like I said, PCA is the linear regression equivalent of supervised learning in unsupervised learning, in my opinion. It's like the old school statistical technique that works on lower dimensions, but when you scale up the dimensionality, then you start using techniques like UMAP, like TSNE. I feel like all of these things are just named as acronyms. I don't think there's any exceptions. VAEs are another technique, variational autoencoders, and those are based on deep learning, and that's really, really cool, and they can do some awesome things.
Yeah, maybe say a bit more about VAEs or even just the general idea of an autoencoder, because I think the idea of compressing down your input into the most important features almost will come in useful when we start to discuss the ideas of I will fuck it up every time, self-supervised learning.
There we go. Editing magic will have to be done.
I don't think I should be edited. I should just be punished until I get it better. Go.
You should just be punished. We're gonna label you with shame,
yep.
and then you have to update until you get your parameters correct. All right. So an autoencoder is a kind of neural network that is structured. We would use the term architecture. It has the architecture that allows you to do dimensionality reduction using the same feed-forward neural networks and the same backpropagation for learning that all other neural networks use, right? And neural networks are really powerful for a number of reasons. They have a lot of really, really cool properties, and they benefit especially from modern advances in dataset size and computing power. Like, there's competition when you're using small datasets and simple problems among which algorithms are best. And a lot of the old school statistical approaches work very well. But as you scale things, almost always, and this is why there's been such a boom, almost always, deep learning with neural networks outperforms everything else. And it outperforms everything else like consistently. Like if you keep giving it data and computing power, it keeps getting better. It doesn't taper off. It plateaus a little, but it's more like a logarithmic curve, right? So this is why autoencoders are so interesting. It's because you're taking that really powerful concept that we've developed in neural networks and all the valuable properties it has, and using it to do this problem of dimensionality reduction. And so what you can imagine, and I think we'll probably link to like a useful graphic or something, or listeners can can look this up, if you look at like architecture of an autoencoder, what you'll see is that it is a neural network. So you've got nodes that are connected by edges, and these come in layers, like in every neural network. And just like many neural networks, they tend to narrow down, right? So your first layer has lots of nodes, and each layer you tend to sort of decrease the number of nodes over time. And in the case of, say, a convolutional neural network, this has some other added complexities, but this funneling technique is really, really useful because it can take really high dimensional complex things and reduce them into much simpler representations in an abstract space, right? And so what's really cool about autoencoders is you are finding ways to represent the same data almost with fewer numbers, right? Like that's one way. It's a horrible oversimplification to anyone who knows how these things work, but it's a good starting point to think about this. So imagine you have 10 data points, but I tell you that you can put them in my special machine called an autoencoder. It will give you out 2 data points that capture 95 to 99% of the same information. You could think of it like video compression. That's an example, right? You can take this, if you were to just take every frame of a video as an image, right? This is why GIFs can be so large, is because they treat every frame as a full image independent of the previous frames, right? If you were to do that, a video that you might watch in HD would be like a few gigabytes per minute, probably. It's really, really large. And so the reason why we are able to do video on the web at all is because of compression. But these compression algorithms are like hand coded and based on heuristics, and they look at like patterns and edges and things like that. But an autoencoder learns that by itself, by just being exposed to lots and lots and lots of examples. And so what you're doing is you're penalizing it for having too much loss in quality. And what that trains it to do is find a really good way of representing some data very concisely, right? And that is exactly the same fundamental problem as dimensionality reduction. You want to represent the data as accurately as possible, but in a much smaller space with much fewer features. Right, so you wanted to jump in there?
Yeah, I mean, I think it's just worth walking that through end to end. So, as you said, like, you can just imagine a really trivial case here where you give your autoencoder just a list of numbers, right? You could give it the numbers 1 to 10, but each of them is repeated 1,000,000 times. Yep. And so now to send that through would be a relatively big file. But imagine passing that through your autoencoder, and the idea which you hit on there is that you constrict it in the middle. You say, I don't care that the actual list is 10 million entries long, if for the simple list of numbers, but it could be pixels or whatever. I want you to find a way to represent this entire thing using 10 of them. And in this case, it's easy. So now the simplest way in this one would just be to take each number and then also maybe an instruction at the end to multiply each of them by 1,000,000 or repeat each one 1,000,000 times, right? Mm-hmm. But that's really powerful because by placing this bottleneck in the middle, and when you look at pictures of the actual architecture, you can literally see that the autoencoder sort of funnels down where you're asking it to find the smallest possible basis to reconstruct that input image. And then it reverses that funnel back up at the output. And it says, okay, using that representation, can I now build a high fidelity reconstruction, like by minimizing how much detail is lost under the constraint of having very few dimensions to work with in that representation.
Exactly. So it's almost like symmetric. Very often they actually are, is that the way that you undo it is almost perfectly symmetric to the way that you do it, at least in terms of the architecture of the network, right? So you have the funneling down on one end and then you have the funneling back out on the other. And that's how you're able to quantify how accurate the compression is, right? Because you then use it to reconstruct the initial values, and then you compare how those differ from the actual true values. And so you're simultaneously training the encoder and the de-encoder. You're simultaneously training the encoder and the decoder.
The de-encoder, yeah. Now we need to...
Sorry, yeah. And that's my self-supervised, model. Yeah. Exactly. And what's kind of cool then is at the end, you've trained 2 networks in one, and then you can kind of just chop it off in the middle and then use both for interesting purposes.
Say more about the purposes.
Yeah, so I mean, there are lots, but the ones that I've often thought about or seen used are the encoder part you're using to represent this complex data, to do your dimensionality reduction and to find clustering or patterns. So you could use it instead of PCA or UMAP, and it's very useful in that regard. But the beauty is then you can then just map back up. And the extra cool thing about that is that you can just take some point on your reduced space, the output of the encoder, that you've never seen before, and infer where that might be if it were ever to have existed, right? So you can kind of say, if you get two clusters, let's say you run this on your retail chain data from your spending habits of your customers. So your encoder manages to create this two-dimensional output space, and there are three clusters of different kinds of customer on there. Fantastic. It's identified three different types of customer. But now what's awesome is you can go and find any point on or between those two clusters and put that point into your decoder, and it will show you what the properties of that customer would be, even though that customer has never been seen before, doesn't exist, right? So you can now do these hypothetical spaces. And there's a lot of caveats when you do that, because you have to like avoid things that, for instance, if you're doing like manufacturing, which is the domain I did in, you've got to avoid things that literally defy the laws of physics. Like something can't be 1,000 degrees on one end and negative 20 million degrees on the other, literally like impossible values, right? So there are certain things that constrain that space and the ability to walk paths along that space. But it's really, really cool because you get to reverse it perfectly. And some methods of dimensionality reduction don't actually have that feature. You can't reliably get the same clusters out, and you can't reverse it. So I think Teasney has that problem. It's not a reversible process. And PCA, you can reverse it, but it's kind of a hack. You don't actually really reverse it. You just kind of brute force the input, as far as I understand it, and observe the outputs. So it's, I mean, you can do it by reversing the eigenvectors. Okay, scratch that out. But Teasney you can't, as far as I know, because everyone's like, don't use Teasney because it can't do that. And so there are a lot of use cases for these variational autoencoders and the corresponding decoders. And I think like that space still hasn't even been explored completely. Pun not intended, but very spontaneously, but very serendipitous. So I just want to add in one last thing that I think is useful here.
And then I'll jump to self-supervised.
Before you jump in, yeah. Is just that we've kind of touched on two of the major branches of machine learning, and that is, or of AI really, and that is supervised learning, unsupervised learning. Another one that people will often hear about, and I think is worth just mentioning here and just sort of flagging for later work, is reinforcement learning, right? So this is again, like supervised learning is different from unsupervised learning, reinforcement learning is different from both those two. And reinforcement learning is what drives a lot of these really interesting advancements in like playing chess and Go, like all the Alpha Go, Alpha Zero, all of those kind of things, the open AIs, Dota playing systems, all of those are based on reinforcement learning. And reinforcement learning tries to emulate more how real entities learn by engaging with their environments, and maybe is a better approximation of how brains learn. But there's way too much complexity to dig into that. But I just want to put the flag there and say that is also another domain, another maybe branch of AI.
Yeah.
But it does some really cool things. But for the most part, like 90 to 95% of what gets used in industry, like in, retail or those kinds of systems, is supervised learning and maybe a sprinkle of unsupervised learning here and there. Like most people are using supervised learning when they say they're using ML.
It's worth jumping in there and asking, I mean, in your opinion, you've sort of worked in this industry a little bit. I look at it and I think that the next sort of frontier of problems are going to be very amenable to people doing much more RL, the reinforcement learning side, because of this ability to look more at domains where you can just design some sort of reward and then optimize on that, instead of this kind of inference-based paradigm that we see in deep learning, right? Where you're just trying to predict something, whereas reinforcement learning always feels much more like actual AI to me, because it's predicated upon action in some sense, right? So I just wanted to get your quick 2 cents on that, and then we can continue.
Yeah, I think there's a lot of interesting advances to be made, and I think there's a lot of unexplored space in reinforcement learning and unsupervised learning still. But supervised learning is probably going to be the most useful to your average business, right? Like if you've got data, which most like online services do, and you've got some money to throw at a company like Amazon or Google or maybe Microsoft, they've almost got like off the shelf supervised learning. Like the field is so mature in that side of things that it's almost like plug and play these days. It's like Lego. And it's obviously, you don't even need to hire anyone to do it for you. You just like sort of buy the package online and throw your data at it, and it does predictions. And that's very useful, and it can lead to a lot of value to companies, to businesses, in terms of profitability. But yes, I think in terms of the sea changes, in terms of the breakthroughs, in terms of the paradigm shifts, 100%. A little bit of interesting stuff still to be explored in unsupervised learning, and a lot in reinforcement learning. And I think of all domains, reinforcement learning seems to hold the most promise for generalizable intelligence. Like supervised learning is very good at getting crazy good at narrow tasks like identifying objects, but that is only part of intelligence, right? And so when the reinforcement learning comes into play, then you start getting into real AI as it's been envisioned in science fiction and popular culture for decades. So and really cool meaty research.
Yeah.
So yeah, that's the stuff I'm excited to play around with. So yeah, so jump into self-supervised learning here.
I'm glad you can say it on the first try. So I mean, I think the first thing is as you say, is what it is, and then maybe motivating for why we need it. So I mean, the general idea is sort of like unsupervised learning. You're wanting to train this model that you've got based on some sort of label that like is naturally part of the data. So what you're trying to do is do a kind of pre-training where the model learns features that are actually relevant to the data. So there's 2 examples that are helpful. The first one is just as to what I might mean by a natural label. So most language models that are used today have this kind of element where if you want to train it to understand human language, you don't need anyone to label your sentences. You can just give the machine a bunch of sentences and then say, cut off the last word of every one and get it to predict the next word in the sentence as it goes, right? And then the label becomes just what the actual word was, right? So, I mean, if I start saying the cat sat on your brain has a probabilistic prediction for what the next word is, right? Aside from the fact of preschool. And I didn't need to give you any labeled training data. If I then show you that the last word is mat, then you can update towards thinking that the words cat, sat, and mat are more likely to occur together in the future. So that's the sort of label that's naturally part of the data, right? So this has been in use with language modeling for a couple of years now, although it's fairly new. And the motivation behind this is like, can we do this for more domains? And the domain that I focused on was images, because there's a lot of images out there if you think about it, right? I mean, the internet is full of them. But as you pointed out at the start, to use a lot of these, you need labeled images. And this is just time consuming to make. And especially for some sort of narrow domains in deep learning, where there's not much in the way of big public data sets, it can be really difficult to make an accurate model with so little data. So I mean, like deep learning, I think a lot of people know by now, has this really big problem with size. I mean, the ImageNet data set contains something like 14 million images at this point. And obviously that's now split into lots of classes. But the point is to get a model which is really accurate still requires a lot of labeled training data, which you might not be able to get if, let's say, the thing that you wanted to learn to predict was something which only happens very rarely in time, or where you can't afford to employ an entire team of people to label every example you've got. So what self-supervised learning might look like on images would be, if you think of a normal convolutional neural network, how if you train it fully supervised on ImageNet and you look at what features it learns, and you can just look at what the filters look like, right? You can visualize them. You sort of see that in the first few layers, it kind of learns edges, and then the next layer up, it learns combinations of those edges. And then as you go through up the network, it's got more and more complex features, right? And these features act as or feature detectors in the input image, right? So it might
absolutely
fire really positively on the edge of your face, and then there's like a nose feature which detects noses and eyes and everything else, right? And what, in the same way that a good language model could be built by learning to predict the next word in a sentence, because that means that you've learned something about the structure of language, a good self-supervised image learner would somehow learn something about edges and combinations thereof, but without this training paradigm that we use where you give it a lot of labeled data and then it does that, if that makes sense.
Right. Interesting. Very, very cool. So I'm by no means very informed on that branch of research. One thing I do just want to sort of caveat here is to say that people should not be confused between two terms that I think could be confused here. So self-supervised learning is what you're talking about now. And that shouldn't be confused with semi-supervised learning. Self-supervised learning is like a variation on supervised learning, as you've just explained, in that you there is still a label. It's just that you're not having to get the label from humans manually doing the work in the simplest form, right?
Right.
There's more complexity to it as well. But semi-supervised learning is more like a variation on unsupervised learning. And it's quite a distinct thing. So I think just to be aware of the difference in terminology there, I think there's a very different approaches, even if I have oversimplified them for the purposes of this.
I mean, say more about semi-supervised learning then, and I'll make sure that I'm not getting the terms confused in my head before I talk more about it.
Oh no, I doubt you are if you've just done a project on this, because you would have been researching the literature and things like that. I mean, but
in a week.
so semi-supervised learning is not something that I've had much experience in either. But as far as I understand it, what you're doing is you're passing in some information to show what you care about into an unsupervised learning system. So it's maybe not the ideal name. So in other words, you don't have to go and manually label a lot of data, but you can put in hints about like things, properties of that data that you might care about to assist the unsupervised learning in identifying clusters that are useful to you, or in performing the kind of dimensionality reduction that aligns with what the data science team cares about researching in this particular problem. So it's just ways of adding in like extra little information in a extra information from the developers to get the algorithms to produce the kinds of results that they want.
About. Right.
Without having to label the data. Yeah, exactly. So it's like a variation on unsupervised learning. Whereas what you're speaking about sounds to me, at least in the context of like language, sounds to me much more like a variation on supervised learning.
I guess I can kind of see them blending into each other.
There's that gray area, right, where they start overlapping. And I think that's where things get super interesting.
Yeah, because if you think about it, so once you've trained, let's just take the language model example, right? It's learned something about the statistical structure of data on its own. And I guess the semi-supervised part of that is you've told it what you care about is the next word in the sentence. So it's trying to learn now spatial or temporal relations. So that's kind of semi-supervised. And then the reason that it becomes a kind of self-supervised thing is because at the end of this, you're going to actually give it labels on a smaller subset of data. And you're going to rely on the fact that it's learned a general language model. And now by giving it relatively few labels, it'll also now learn to characterize or to label unseen examples well, which it wouldn't have done without that self-supervised language model that it had to learn on its own.
now I see where the interesting gray area is between the two, because you approach one from the supervised side, you approach the other from the unsupervised side to some extent, but they almost conceptually end up converging, at least in our interpretation of the models. And this is where it starts getting me really excited. Okay, so the self-supervised learning that you're talking about is almost a way of, and I'm going to throw in a term that's become almost entirely useless, bootstrapping your data labeling, right?
Right.
And the phrase is totally useless because everyone loves it, because it describes this way you might pull yourself up by your own bootstraps, right? It's like, maybe we should call it sky hooking, just to throw in some other overused phrases here. All right, so talk a little more about it then.
Well, what I'll do is walk through maybe some of the previous ways that this has been done. And there's a really good blog post by Jeremy Howard on the Fast AI blog, which also does this really well. So that's definitely worth checking out. Awesome. Because it's got links to some papers, it's got nice images. But roughly speaking, if you think of images, right, what we're trying to do is teach our model to understand something useful about the internal structure of images that come from our universe, our world, right? And so a really natural one might be to try and take advantage of temporal structure in your data. So this would be really easy with like a video, right? So if you have a video of someone taking some action, previous attempts do something like take the frames, then mix up the order of the frames, right? So, someone's pouring some water and mix up the order. So the first frame is now the water is full, but now the frame after that is someone pouring it into it. And just make a model that tries to predict the correct order. And basically that's, again, trying to do the similar thing to what the language models are doing, right? Because if it learns to put things in the correct order, what you're assuming is that it's also learning something about the structure of the world, right? It has to know that, first of all, something about the water being poured has to precede it filling the glass, which means that you have to have this kind of internal representation of water, possibly. Another really interesting one that I saw was where and again, all of these techniques are basically just trying to do something so that you're forcing the model to learn something about what real images are and what isn't a real image. And in doing so, it has to have this internal model of the world in some way. So a really cool one is you take your training data and half of it you apply random distortions to, so you could make it fuzzy or mess up the color or blur it out. And then the other half you leave normal. And then you just train just a prediction model. And the prediction model just has to say, is this a real image that wasn't distorted, or is this one of the distorted ones? And again, that's
right,
naturally labeled because you just know which images you distorted. And again, to do it, you have to know the difference between something distorted, i.e. unreal, and what a real image from our world looks like, which means you've, again, got some sort of feature. But then I guess what this all builds up to, and what the sort of holy grail, as far as I can tell, in this place would be having a fully generative model for your data. So I think what people dream of doing is you give, in the same way where you block off the last word in the next word in a sentence and then say predicted. Imagine if you could just pass the model an image, block out some of the pixels in that image and say reconstruct the full image, right? Because that's the most natural way to do this. And the problem with that, so that would be almost the naive approach. If you're just trying to fill in pixels, then that doesn't really work so well. And my intuition for why is because you're not really forcing the model to learn a feature. You're just kind of placing pixel values. So you can do it over bigger segments. And the ideal would be to have this generative model. So instead of filling in individual pixels, you're filling in edges and lines and curves, right? These sort of more atomic pieces that make up the world. But the problem is that the image, an image is really high dimensional. If you just cut out a few pixels, a square, the number of different values it could take is just so big that you're just trying to brute force a problem, which is going to be probably intractable. So basically, this problem of trying to find a generative model is solved in an interesting way by the main architecture, which I sort of looked into a little bit more. And this is an architecture called CPC, which stands for Contrastive Predictive Coding. And it's really worth getting into. Also, yes, it's predictive coding or predictive processing, which we still haven't talked about here after so many hints about it. So,
oh man, I think we've mentioned it more than Eliezer Yudkowsky in the last few episodes. Like,
maybe this will be the episode that forces us to sit down and prepare for the next episode when we do it.
So what I want everyone who's listening to this right now to do is go onto Twitter. Sign up for Twitter if you don't have it.
And
go onto Twitter
Gianluca,
and
yes.
go to Jared's profile. The link is in the show notes at JNearestN, I think it is.
Yeah.
And just rage tweet him until he finally gives in and sets the ball rolling for this predictive coding episode. Just bully him. Just straight up cyberbully him.
Yep, cyberbully me. We need more of that. Twitter's become too nice. Everyone's too soft. Yeah, I mean, just hit me with your quick reaction on those basic ideas. I think they give a really nice intuition for what we're trying to achieve with self-supervised learning.
Yeah, man, it's super cool. So you have mentioned elements of this to me before, but like there's always a time and a place for things when they can impact the best. And I think the bandwidth limitations on our video call this evening maybe obscured the fact somewhat from you. But while you were talking there, I did literally have my eureka face and then furiously start scribbling notes because I realized, and presumably someone else has had this realization because it was like one or two inferential steps at most from what you were talking about. But I had never realized it before. When you're talking about the system taking the video of someone pouring water that had been shuffled up so that the frames were out of order and trying to correctly order the frames, the idea that immediately occurred to me was that this could be a great way of dealing with small data sets, which is usually the kind of thing you have in domains that I am interested in, like quantified self.
This is what I was trying to say at the start.
Yeah, right. So this is exactly okay. But the reason why this is interesting is so like the current little project that I'm focusing on is to try and create predictive models for my sleep data. So I've got like, many nights of sleep data, but a few hundred, not a few million, right? So you can't just throw any deep learning approach at this. And then I've got some other data like exercise information, heart rate, alcohol, caffeine logs, those kind of things that I can then use to try and predict the sleep. And the reason I want to do this is because if you have a predictive model, then you can start reverse engineering to see what factors influence sleep, and then you can do interventions. And this is where the whole quantified self, individualized medicine frame space gets interesting. And more to come on that soon. If you want it sooner, rage tweet at me. But the idea that I had was, what if you just did the problem by just shuffling the output, like the sleep data, and then you just assigned the system the task of matching the input data to the correct. Like, you remember when you're a kid in school, and one of the ways they could ask you questions was to have you just like match pairs of things. So you get like two lists of things, and you just have to like draw lines matching up which one goes with which one.
Right.
Like, imagine that, but for a kind of supervised learning problem.
Wait, so what's your input and output here? I'm not sure if I...
So my input is going to be like all these parameters about my daily life in this case, right? So it's going to be like exercise, logs of when I had alcohol and caffeine, when my feeding window was, all of these kinds of things that might influence my sleep quality. The local weather where I was, time, or yes, current season, all kinds of information like that. And then the output data, the thing I'm trying to predict, is the quality and quantity of sleep, which you compose into a single score, right? And instead of trying to just do it as a supervised learning problem, where you will either overfit to your tiny data set, or you just won't be able to learn any pattern because you've got too many features and too little data. One way you might do this, and you would probably need some other transfer learning or something to get you started, perhaps, but would just be to shuffle the output data. So instead of having them as labels, you just treat it like those frames of the video that are out of order. And then what you try and do, or predict the next word, right? But it's got all the options there, right? And so it's like, okay, given that I went for a run today and I drank alcohol at 4 p.m. and my last cup of coffee was at 3 p.m., which of the following nights of sleep do you think followed? Like, was it the night that I slept for 2 hours? Was it the night that I slept for 10 hours? Was it the night that I slept for 6 hours? Right? And it's got to try and pick which one. But not only pick which one, it's got to try and order them for each case. Because you're now getting a lot more information out here. Because it's now ranking them in terms of probability, just like the predictive model for the next word.
Doesn't this feel kind of just like supervised learning? Or am I missing something?
I mean, the supervised thing hasn't come in yet, right? Because it's the same thing as what you're doing with the video that has frames out of order. Is you're trying to now figure out ordering, because like the sequencing of things is what's interesting here. But my point being is that you would get an ordering, and from that ordering you could infer some kind of approximate probabilities. Right. And so suddenly from very little data, you're getting a lot of information, because now you're getting almost like it's become a Bayesian system instead of just being a kind of one hot system. Or instead of inferring your degree of belief from the output value and how closely that, like how, I mean, with regression, you have no way of doing that. This would be a regression task, and you have no way of quantifying your degree of certainty in a simple regression system. For classification, you can, right, from the output feature, right? But with regression, you can't. And so this would be a way of then taking a regression problem and turning it into kind of like a Bayesian probabilistic model of like probabilistically, right? That's maybe the wrong framing to use, but it would be a probabilistic, it would represent the degree of belief that each of those, so maybe a way to think about it is you would have some probability mass distribution over all the possible nights of sleep. And so then you could just look at like where most of that mass is clustered. I don't know. I mean, this literally just came to me as an interesting thing to explore. Yeah. So I'm probably talking total bullshit, but who knows?
Yeah, I kind of see it. I think what you're trying to say is you're trying to figure out what are the possible values here, and is there some sort of internal structure to how? Yeah, I'm not seeing it fully, but maybe it's just something that I have to think about more.
So the classic supervised learning would just be you. Let's pretend you're the algorithm, you are the learning model, and I am the researcher, right?
Right.
I have all the cards with the answers on them, and I now say to you, okay, here's some information. What do you predict? And then you say and you guess something, and then I show you the card that was the right answer, and then you learn from the difference between the two. Whereas, so what I'm proposing now is that you instead go, I have all these cards, and I go, okay, here's some information, some context for you, and then I lay all the cards out in front of you, and I say, order these by which ones you think are most likely the correct answer in like descending order of likelihood rather. And then by doing that, I now get a sense of A, what you've learned, and B, like if you have like the top 10 are all 6.231 hours sleep, like, you know, and there's got very little variation in them, then I can be like highly confident that that is an accurate prediction for those kinds of outputs. But if it's like super distributed over like 6 and 10 and 3 hours, then I can be pretty confident that you have no clue what you're talking about. So it gives me a way of adding probabilistic information to a supervised learning regression task where you're trying to like predict some value, not classify things. And so, and the ordering gives me like, I'm just getting so much more information out of every prediction than I would if you were just giving me a guess as to the number. How you would actually implement that, I'm not entirely sure of. But
yeah. I mean, I kind of see that. I guess because the way you structured it, like your data doesn't really have like a sort of spatial or temporal element to it, right? I mean, obviously it's you know, there's like seasons and stuff, but what you're trying to predict is a quality
That is that's one way I might structure the data. And another way I might structure it is as a continuous time series.
See, then that would make more sense to me, because you could sort of start to try and predict maybe parts of that time series. And yeah, I think obviously you have a much better sense for what your data looks like than I do. So I'm just not catching you here.
The fundamental difference between this and what you were talking about with the video of someone pouring water is that the same 3-second video of someone pouring water can be chopped up into frames and shuffled in various different ways. And so you're getting that like augmentational advantage from it. Whereas like what I'm saying, there's you can shuffle it in various ways, but it's still the same problem that it's seeing each time. But there's like some core commonality there that I just thought was really interesting enough to like get excited and write it down. And I'm definitely going to try and explore that.
Yeah, well, explore it and then tell me about it.
But yeah, but the self-supervised thing is super cool because of its potential to like you were speaking about with hypothetically images being a fully generative model. And when it comes to very small data sets and trying to use these cutting edge machine learning techniques, if you have generative models, you can use very small data sets to synthesize large data sets, train these massive models on the large data sets, and then just fine tune them on the real data, which allows you, hopefully, to actually create a strong, robust, generalizable model without overfitting.
Yeah.
Maybe it's a pipe dream, but there's definitely that hope. And it would be super useful. So I don't know if you have any more ideas relating to that. I need ideas, damn it. Give me ideas, Jared.
Talk about what this CPC algorithm does, because interestingly, to try and solve this problem of having a generative model over this really high dimensional data, they have this genius idea where they take the generative model and they just make it so instead of having to put your problem in terms of having a generative model for those pixels, you make it into a classification problem. And that's such a clever idea. So I'll try and get at how that works. And then if I fail to do it, it's most likely because I've failed to understand what I'm actually talking about. So
just quick interjection. Do we need to maybe explain, now that we've mentioned it a few times, the difference between regression and classification?
Yeah, hit that out, because there's at least one person who will say thank you.
Yeah. Okay. And yeah, just it's a useful thing to know when throwing these terms around. So when you're talking about supervised learning, there are primarily two different types of problems you can have. The first one is classification, which is like the example of classifying cats and dogs, is where there are a set number of classes of outputs that are possible, and you are trying to predict which one, right? And the cool part about that is that your networks usually give like not perfect values on their output. So if you were predicting cat or dog, it might give you like 0.8 cat and 0.2 dog. And some people say that you can then use that as your degree of belief if you haven't passed it through some other activation function or softmax or whatever. But with a regression problem, you are trying to pick some generally continuous value. I guess it could be integers only, but mostly, some kind of continuous value. So you don't know. There aren't like some set fixed number of possible outputs. It's like trying to predict height or something. It falls on a continuum, and the way you then tell whether you were right or wrong is by comparing the difference between the true value and the predicted value. And you'll use something like mean absolute error or mean squared error, which are literally what their names say, to try and quantify that difference. Whereas with classification, you literally go, was it a dog? No. Or yes. And then you know how to update. So I think that explains it.
Yeah, that's the basic intuition.
All right. So back to you turning it into a classification problem.
Yeah. So as a basic recap of what we're trying to do, we're trying to learn something about the structure of images, right? That's what our self-supervised task is. And we said that the problem with having a fully generative model that can do this is it's high dimensional and maybe it just won't work. And so what this paper does, and we'll link to the papers, they're both on archive that I sort of looked at for this. They're actually like really manageable because I read them, so it can't be that terrible. So basically what you do is, like, imagine you've got an image and divide that image up into patches, just little squares, right? And you just want to choose squares so that like every square overlaps by like half with a square next to it, right? And now what you do is you take each patch and you run it through a normal neural network architecture. It could be like a ResNet, or I think they used a ResNet, but anything that has sort of convolutions, right? And you just set up that architecture so that the result of passing the patch through that architecture is to turn that patch, which would be, you know, sort of like a two-dimensional matrix. You just turn it into a very long vector, right? And that vector now obviously encodes everything in that patch.
Okay. So it's like unraveling a sweater into a single strand of yarn.
Exactly.
Kind of thing. Cool.
So once you've done that, then you've got one of these vectors for every patch in the image, right? So you could imagine having the top row of the image encoded as these vectors. And then what you do is you then pass those vectors into a second network, which they call the context network. And basically that network, now you take the output of that as being, well, the context, as in the same way that saying the cat sat on is the context which you use to predict the word mat. You use these vectors that come out as the context to predict vectors below you. So imagine again that patch, that image divided up into patches, right? What you're doing is you're saying, like, if I've got some vector, which is now this encoded version of a patch, what you do is you say, okay, pick, like, at random, first of all, pick the vector of the patch directly beneath me. So that has to obviously have something in common with me, because first of all, the patches overlap by 50%. And also, you know, like the vector that would encode your nose is going to be like quite closely related to the vector that encodes the piece of skin between your eyebrows, right? So they have their spatial structure in common. So what you say is, okay, you've got this vector that here we're saying is the skin between your eyebrows. And what I want you to do is I want you to learn to predict what the vector directly beneath that will be, right? In this case, your nose. And here's the classification part, because what you say is, I'm going to just sample at random other vectors in this image, and all you have to do is tell me which is the right one. So to do that, you have to have like learned some model of like the internal structure of images. Like you have to know something about why noses come below eyebrows, because you can't just return your hair. That would be like the wrong vector to return. So you, instead of having a generative model where you have to fill in pixels now, you have to just classify between different vector representations of the input image. I don't know if I've done a very good job there. It was a bit too convoluted.
So this list of vectors, of possible vectors,
right,
become your classes for each prediction. So you've got for each case, you've got this list of vectors that you had produced by doing the tiling,
right?
Well, that overlapping tiling. And then what you're trying to do is classify, like each one of those becomes a class, and what you're trying to do is predict which one it was. Am I misunderstanding you?
Yeah, sort of. So it's as you say, so you pick some vector, like let's say in the middle of the image at the top, right? And then you say, like, your job is to now, given that, right, the network's job is tell me what the vector of the patch directly beneath that is. And the options to pick amongst are the actual vector that is there and a couple of random ones that I picked just so that you can't.
Right. Okay.
So it becomes classification because you're just picking amongst a limited set of options.
Yeah.
And then you can take a loss function of this because, again, the label is inherent. Like, you know which vector was actually below it.
Exactly. Okay. That's really, really cool, because the classification then is, I think, an easier problem a lot of the time than regression, right? Like if it had to fully generate all the values, it would be quite difficult. But it's benefiting from having some structure there. So the fact that it's just like multiple choice is easier than open-ended questions in some sense.
Yeah, that's
unless
a really
the
good way of putting
person
it.
who sets the test is deliberately trying to trick you. And in this case, we kind of are. We're trying to make sure that the student knows what they're talking about without having to make them memorize whole long things, right? So we're helping them to learn effectively and not just cheat. Like, we don't want students that just memorize what kinds of bullshit essays to write. We want students that actually understand concepts. And it's almost like we're creating a better test or examination that will help facilitate that.
Yeah, exactly. I mean, if this is not clear, and that's entirely my fault, I will make sure to link in the show notes to a couple blog posts that make it quite clear.
Do they have some good like visual illustrations of this? Because I feel like that was what will really help solidify it.
This is easier with a visual illustration, for sure. Maybe I was ambitious, but like the central idea of, you project some patches using a ResNet, you make them into a vector, and then you say, given some vector that's at one space in the image, can I predict which vector is directly beneath me from a set of other vectors in the image, right? And only one of those is the right one. That itself is fairly okay. And then the loss function is actually not super ugly, like it reads at least. And the papers that describe this do a really good job, I think, of being really like reasonably concise in talking about some of the intuitions behind this.
Yeah, it's augmentation for your target feature as opposed to for your input data.
Yeah, say more about that,
because
that's a really, really cool idea. And I think you've hit it on the head there.
Okay. And this also just gave me a more refined version of what I initially suggested for my project. So I'm super excited about this. All right. So data augmentation is just ways of taking existing data that you have in your data set and modifying it in slight ways such that it's still valid data, but that you just now you can use them as separate examples. So if you've got a data set of 1,000 images, that's not very much, right? Let's say 1,000 images of human faces, right? So you go and you have 1,000 different people and one photo of each of their faces. And now you want to make a system that can tell them apart. You're probably going to struggle because that's just not that much data. And it only has one example of each person. So the canonical types of things you would do there is you would go and rotate the images for starters. So you would do all various like rotations of them. You would like zoom into parts of the images. You would apply like noise over them, like white noise, so it looks a little bit like hazy, like a static on a television. You would like change the color. You would like hyper or desaturation. There's all sorts of augmentations you can do, and there's libraries out there of code that you can just click. Pretty much you just tell it what kinds of augmentation you want it to do, and it will automatically do this for you. Because the label stays the same in all of these cases. So once again, you're not having to go and label all of these things. So you can take one photo of, should we use Alice and Bob in this example? Because those are classics of computer science. You've got a photo of Alice, you've got a photo of Bob, you've got one of each of them. Now you go and you augment in these 9, 10, 15, 100 different ways. And now you have that many examples of a picture of Alice, of a picture of Bob. So your system is much more likely to learn the actual signal there because you're adding in all these extra kinds of noise, of variation, of things that could confuse it, but those help it learn to differentiate the faces better. I've never actually done it with trying to do facial identification, but I presume that would work. Anyway, that's image augmentation, and that's one kind of way you might augment data. It's the most tangible way, right? So it makes for a good example. That's augmenting your input data, right? The data that you give to the model, right? But what we're talking about in these contrastive predictive coding systems is kind of like augmenting your label, augmenting the target feature, right? The thing that you're having the model predict as opposed to the thing it's learning to predict from. And so instead of just giving one label every time, you're giving options, one of which is the correct one. And we know that obviously. And some are other ones that come from legitimate parts of the data. Maybe you throw in some ones there that are just completely randomly generated, who knows? But it's a way of creating augmentations of the label of the target and thereby improving the quality of your learning, which I think is a really, really cool idea. And the refinement to my initial suggestion on the sleep model is, instead of having it do the ordering, what you would just do is, for every day that I have like data for of input things like exercise and caffeine and alcohol and whatnot, you would then show it like 3 or 4 or 10 or 15 options of randomly selected nights of sleep, as well as the actual one that was the correct night of sleep. So the others are all valid nights of sleep, just not the ones that correspond to that day in the real data set. And then you would have it predict which one was the correct. You're turning it into a classification problem. And the beauty there is I can still get, I mean, there you're getting the weights, the strength of its outputs for each of those classes becomes the approximation of its degree of confidence. And you can use that as a signal to see how well it's learning. And I think that gives more information, because also you can look at the qualities of those nights of sleep. You could also sample them in a intelligent way as opposed to randomly sampling. So you could sample according to some kind of normal distribution. So if your target, the true label, is the mean of your distribution, you would then sample around that so that you have a lot that look similar to it and a few that look very different. And maybe that makes it more challenging and that creates a better model. You could also maybe synthesize new ones from the same distribution, something like that. So that I think could be a really interesting space to explore, which is not exactly like these CPC systems, but it has that similar feature of augmenting the target, which I think is a really interesting idea.
Yeah, I think it's worth exploring that. And I mean, I hope that when you
definitely
start working on that, you come back and tell us a bit about it.
Yeah, I'm going to check out those papers that you mentioned.
Yeah, definitely. I think what we'll do is I'll just mention sort of like the kind of results that this is getting, and then we'll start to wrap up.
So at the beginning, you said that this is what you did the final project on?
So, well, yeah, my final project was just looking at this and trying to look at its like data efficiency. So, okay. Like how few.
Yeah. So I mean,
labels.
Maybe talk a bit about that as well, as we sort of wrap things up here.
Yeah. So, I mean, the crux of this, right, is if it works, then you should be able to solve in part that size problem that deep learning has, right? Where you, instead of needing millions of labeled training data examples, you might be able to get away with far fewer. And if you look at some of the graphs in the papers, it's striking the extent to which these models can do this. So they can outperform like a standard ResNet on ImageNet at like fully trained with all the labels, but they are very robust to a decreasing label percentage. So like the ResNet accuracy falls off precipitously, even if you drop its training data label percentage by like 20%.
Okay, so maybe just unpack that a little. So what you're talking about there is ResNets, which are one kind of convolutional network. You train them, right, but you train them many times over independently, the same network, but you train it on the same data set many times over, but each time you remove some of the labeled data from the data set. So it's just fewer examples, or just you're taking away the labels?
No. So what I'm saying is, so what you're just doing here is you're comparing how does my accuracy change as I give the network less and less training data. So like you could train one and you
just straight up fewer examples.
Yeah. So like to give it one where you've got every label, then you halve it, and then you could maybe give it 25%, and you train different networks here and just compare what their output accuracies are. And you can do the same with CPC.
So you're literally just like throwing away some of the images in the data set each time? Or are you just removing the labels somehow? You're just throwing away images. So your N just gets smaller. Your number of examples just gets smaller, or what?
So with CPC, obviously, because it can train sort of unsupervised on the unlabeled ones, I guess you're not throwing away the images. And then for the ResNet, because, it relies on supervised training, then the unlabeled ones would be kind of meaningless.
Okay, I see. Okay, got you. So it respects the distinction with how these two different systems operate. So they still have access to all the images, except the regular ResNet supervised learning can only use the ones that have labels, obviously. And so as you remove some of the labels, it just can't use those images at all. And so whereas the CPC can still make use of them.
I mean, I guess another way of doing this is just like, let's say you had, 1,000 training images. You could just split that like train and test, and you could just change your train test split. So you could just say like 20% are training. That I think is probably how you do this. If you want to
having a different test size would probably skew your like accuracy scores somewhat. So you'd maybe need to like limit that somehow. But yeah, okay, I get what you're saying now. I just wanted to clarify what you meant by as you reduce the label percentage. Okay.
Yeah.
But essentially, what you're doing is you're saying, oh, how well do you do when I give you all the information? Really well. Okay, now I'm going to start taking information away and retraining you each. Like it's a new network every time, right. And you just quantify its performance each time. And as you're removing them, the ResNet decreases in performance dramatically. So. Just falls off a cliff.
Yeah, it's
pretty much. Okay,
it's not robust at all, right? I mean, it's the classic example of being data hungry. But CPC trained on unlabeled data and then given these like low label percentages is strikingly good. I mean, I don't want to actually say an actual number now because it's going to be wrong, but I will link to the graph in the actual paper where they look at this, and very quickly it is outperforming the ResNet by a big margin. And that margin is solely due to the fact that it's robust to this decrease in percentage of labeled data.
Okay. So it is making use of the data of the labels when they are there, but when they're not there, it can still use.
So no, now I've been unclear. So how you train these things, obviously, right, is so you first do like a pre-training round where you just give it unlabeled data entirely, right?
Right.
And there it's doing this sort of prediction thing where you're trying to predict the vector beneath it that we spoke about. And once you've done that for a little while, you, like as soon as the network converges and you have done this kind of unsupervised training, then you basically save the weights of that model, and that's your pre-trained model. And then what you want to do is on top of that pre-trained model, you just add like a linear classifier, and you do supervised learning on that with like the desired percentage of labels. So, which
is literally just telling it how to name the things. Essentially, it's just learning our names for the things, right?
Exactly.
Okay. So you're just adding like a simple network right at the end. That's just a basic classifier, and just learns to map the the CPC network's names for things onto human names.
Exactly.
Okay.
Exactly. So that you just do normal gradient descent on at the end, and it's just got labels. So basically what you're comparing is this pre-trained CPC architecture at low label percentages to a ResNet at low label percentages. And what you're seeing is the effect of doing this self-supervised learning, because if it has worked, then you should basically be able to do better accuracy prediction even when you don't have many labels for your data, because you somehow know more about what images are, even with fewer labeled examples.
All right, I see. Okay, so the only thing that's really differing for the CPC is just that final linear classifier at the end. That's just getting less training data every time. But the rest of the CPC doesn't even notice that you've done anything differently in each of these runs.
Yeah, well,
it still was trained on the same data. It's the same data set just because it never saw the labels anyway.
Yeah.
So it's only that linear classifier that you're tacking on at the end that's getting less and less labeled data. And so, but because it's already got this really high value representation coming into it, it doesn't need as much, and it's easier to train because it's much smaller than training the whole ResNet. Okay, that makes a lot more sense.
Yeah.
Got you.
So
that's really, really cool.
Yeah, I mean, there's lots to explore here, and it's like really new, especially like the newest stuff. It's a couple months old, so everyone should allow for some misinterpretations here, because I think it's kind of changing underfoot as we go, which is always the danger of talking about something very new. Besides the obvious danger of,
I mean, this whole field is.
But yeah, it's just so interesting. And I think it's almost, for me, it was like worth talking about, even though my understanding is probably sketchy here, because the general idea is so interesting. It's worth propagating.
Yeah, exactly. No, it was, I mean, even just for the fact that you've seeded so many ideas in me that I'm going to be able to practically go and experiment with now in the next 2 months. For that alone, I think it's been worth it. And if that generalizes to anyone else listening to this, then I mean that's been awesome. So yeah, thanks for like digging into it and sharing what you've learned. And there's always so much value to be found in learning something from someone who's just learned it themselves. I think expert opinions are great. And experts have a way of seeing things from different vantage points and connecting disparate ideas. But I think we tend to undervalue how useful it is to learn something from someone who's just learned it too.
Well, yeah, I definitely refined a few things in this conversation where I realized, like, oh, that's why you do that, So I do enjoy trying to hash it all out. So as long as everyone's willing to accept me learning in real time, then that's all good.
Yeah, fantastic.
Awesome. Shall we leave it there?
I think let's leave it there. That's been a really good one, and I learned a lot. I think just speaking about these things combines ideas and crystallizes previously held ones in a number of useful ways. So I've really enjoyed the conversation. So yeah, thanks for bringing in the new subject matter, and it's been a great chat as usual.
Thank you very much, FRB.
Great. Until next time.
Till next time. Thanks for listening to the Bit of a Tangent podcast. We certainly appreciate the continued support and listenership that we've received. And if you enjoyed that episode, please do consider sharing it with just a single friend you think might also enjoy it. That is genuinely the best way for a podcast to grow organically. If you have comments, please tweet us. The podcast is at PodTangent, or you can follow us on Instagram also at PodTangent. Thanks for listening, and we'll see you back here soon.